Hi everyone, our team's topic is to build accelerated neural radiance field. Here's the motivation. So neural radiance fields proposes an innovative solution to the scene representation problem. Traditionally, scene representations are explicit. It requires building a 3D mesh model first and then render the scene. The pro of this method is it has flexibility and control over the 3D object and is computationally efficient, but the con is it takes efforts to construct the scene while rendering can be complex. And neural radiance fields implicitly represents the scene. It generates novel view of a scene from a partial set of 2D images using a fully connected multi-layer perceptron network. The pro is it doesn't require building a 3D mesh model, and it also has photorealistic image output. But the con is it requires a large data set to train the network, and also the simple NeRF models takes too long to train. It can take up to 1 to 2 days to train a model, which is pretty slow. But also there exists many methods to accelerate NeRF. Here are the results of the neural radiance field rendering. We can see that it has photorealistic quality, and also the viewport can rotate in different angles, which are really powerful. Here's the scope of our project. It is divided into two parts. The first part is to build a neural radiance field model from scratch and reaching similar PSNR results as the original NeRF paper. And the second half is to modify the NeRF model and accelerate it using the KiloNeRF method. So the prior works we refer to are the original NeRF paper and the KiloNeRF paper, which can accelerate NeRF by breaking it into many smaller multi-layer perceptron networks. The graph here shows the pipeline of neural radiance field. For the input images, they need to be different views of the same scene, usually captured by camera, and they have really large data size. And they are fed into the NeRF MLP for training. The scene is actually encoded in the MLP weights of the NeRF model. And lastly, after the training, it can be used to render new views. And the input of the neural radiance field network is a scene represented in 5D coordinates. They are spatial locations x, y, and z, and viewing directions theta and pi. The output is the volume density and view-dependent emitted radiance at that spatial location. They are colors, RGB, and sigma, which represents density. Here is a graph showing the multi-layer perceptron network architecture of neural radiance fields. So it actually consists of two MLPs. MLP1 processes positional information, which are X, Y, and Z, and it outputs density, while MLP2 takes the output of MLP1 and processes it with directional information. It outputs color in RGB values. Here's the actual architecture of the NeRF MLP we use. It contains a MLP for positions, which has 5 layers with ReLU activation, and another MLP for directions, which has 3 layers with ReLU activation, a sigma layer for density, and lastly a color layer to output the rendered image with colors. For the model training, we use the MSC loss function and Adam optimizer. For the learning rate, it is exponentially decaying. It starts at 5 times 10 to the negative 4 and decay at the rate of 0.1. For the model evaluation, we primarily look at the peak signal to noise ratio. It's the ratio of the maximum value of the pixel to the noise, which is the MSE, that affects the quality of the pixels. Higher PSNR indicates smaller error, and here's a formula for the PSNR. Here are the results of our simple neural radiance field network. We didn't run it for 100,000 iterations like the original paper did due to limitations in computational power, but the result is still pretty satisfying. The PSNR score of our model reaches 35 after only 8,800 iterations. As a comparison, the original model has a final PSNR score of 40 after 100,000 iterations, so the result is pretty close. And our model takes 3.5 hours on the T4 GPU to run, which is equivalent to 2.4 minutes per 100 iterations, and it is estimated to cost around 24 minutes to train the entire model, which is 1.6 days.
So the second part of our project is called the reimplementation of KiloNeRF. After the regular NeRF was published, there are two main popular topics around it. One is called faster training process of NeRF, since we know that regular NeRF needs hours to days to complete training. And another is how to accelerate the rendering process of NeRF. And the KiloNeRF is one of the methods to accelerate the rendering process of NeRF. Before KiloNeRF, there are some related methods. And one is called neural sparse voxel field, and it uses empty space keeping and early wave termination. These are two very classic techniques, which is also used in KiloNeRF paper. But KiloNeRF tries to reduce rendering time by dividing a giant MLP from regular NeRF paper into many small MLPs. So this is the main innovative point of KiloNeRF. But how does this work? Here are some several steps. Step 1, still based on the concept from the regular NeRF paper, it samples points along the array as a regular NeRF does. In step 2, based on the voxel grid concept, a sampled point is belonged to a cell with 3D index. Step 3, since we define all small MLPs together as a model, we will use the 3D indices to notate which MLP sampled is the sampled point belong to. And for step 2, we do the training and rendering within small MLPs. And for example, in the picture on the right side, if we get a blue sample point located in the cell with 000 index, for regular NeRF, we will input position and pose information of that sample point into the giant MLP. But in KiloNeRF, we will only use this sample point when doing training and rendering of the cell enclosing that point. That means when we will use this blue sample points only to update the parameters of the MLP of index 000. We will not use it when doing computation for other MLPs. And for detailed implementation, how does KiloNeRF accelerate the rendering process? Here are two pictures showing the main structure of a regular MLP, the MLP in the regular NeRF, and the MLP in the KiloNeRF. So it is very obvious that the structure of the MLP in regular NeRF use multiple layers of 256 neurons, while the unit MLP in KiloNeRF use multi layers of 32 neurons. Because the rendering process does parallel computation using KiloNeRF to do forward process for all sample points is much faster than using the regular NeRF. And for the experiment here, we do experiment based on the Lego object in the synthesis NeRF dataset. And we use Atom optimizer with multi-step learning rate. And we use mean square error as the cost function and calculate some criterion like PSNR used in regular NeRF as well. Here are our experiment results. Our PSNR reaches about 23 with 90K iterations, and the rendering time is about 3.5 seconds for one image. And it's much faster than the regular NeRF. Here are some thinking about our experimental result. If we want to get images of higher resolution, we could extend the training epochs since 23 is not good enough for PSNR. However, it is still a time-consuming task to train a NeRF model without any training accelerated strategy. And the second thing is about artifact. Pictures on the right side show the artifact problem when we train a KiloNeRF model from scratch. They're like projection of some part of the object. The KiloNeRF paper calls it artifact, which means something created by the model and something artificial. In the paper, people use model distillation to mitigate this problem, and they use regular NeRF model as a teacher model and train a KiloNeRF model with input-output pairs from a teacher model. And due to time limitation, we don't do model distillation, and this could be something for further implementation. And here is some reference of our project. Thank you.